Hi everyone, Mr. Ray here with our next lesson in logarithms. Uh, so today we're looking at applications. So you've learned a fair bit about logarithms so far, how they're related to exponential functions, how you graph them, how you apply transformations, how you use laws of logarithms and the change of base rule to make your life better in terms of evaluating logs. So we're going to look at how do we apply these logarithms, and there's three very specific applications of these logarithmic scales. Now, why do we need these logarithmic scales or functions or applications? It's when you have it provides a convenient method of comparing values that typically have a very large range. Something like sound levels, where you can hear a mosquito buzzing on the other side of the room, to basically, a rock concert that you're going deaf practically. So how do we provide values that sort of make sense? So we're going to use logarithmic scales. And these logarithmic scales are all going to be base 10. So basically it means every time the scale goes up by 1, it means it's going up, what you're measuring is really going up by a factor of 10. Okay, so we have three applications. We have pH, which for those of you that have taken chemistry, you've probably seen this already. So pH is a measure of the hydronium ions in a substance. Okay, so we have a very specific formula for that, and that's the pH is equal to the negative of the log of the concentration of hydronium ions. So we'll do a couple of question 2 on that. Also the sound levels, we have this formula here. So these would be the sound levels. So we're looking at the difference in two different sound levels and comparing it to the sound intensity of those two sounds. So this one's a little more complicated, but we'll show you a couple of ways we can use that formula. The other formula, it's not in this key concept, but it's the Richter scale for earthquakes. So basically that's something that the ground movement can vary from barely noticeable to tearing down buildings and destroying the earth. So we need a more convenient scale that's going to put that into logic. So if you remember the Richter scale, again, it's base 10. So if you hear that there was an earthquake of 6.0 on the Richter scale, and then another one was 7.0, well, it doesn't sound that different, but it's actually 10 times more powerful because it was 10 to the power 1 difference. Okay, so let's there won't be any application questions outside of that for this course, so it's really just memorizing the three formulas and knowing how to apply them. Okay, so we're going to look at pH scale first. Okay, so reminder, there's your formula. H plus is the hydronium ion concentration. In terms of units, it's measured in moles per liter. So if you know the pH scale, 1 is the low end, that's really acidic. pH 7 is neutral, neither acidic or alkaline, and then pH 14 is extremely alkaline. So the scale just really goes from 1 to 14. All right, so it says tomato juice has a hydronium ion concentration of approximately 0.0001 moles per liter. What is its pH? So we've got the formula for that right here. So it says the pH is equal to the negative of the log of the concentration of hydronium ions. So that's equal to negative log, and we go grab the number. So 0.30 is 1. Okay, and definitely this you can do on a calculator. So the log of that's going to be a -4, but we have a negative in front of that. Be very careful. You'll never have a negative pH, so this number you get here will always be, the log you get here will always be negative, which makes your answer positive because it flips the sign. So that therefore the pH of tomato juice is 4. So that tells you, you know the scale, that between 1 and 6 or less than 7 is on the acidic side. So tomato juice is acidic. It's not alkaline. We also have blood that has a hydronium ion concentration of 4 times 10 to the -7 moles per liter. Is the blood acidic or alkaline? So we're actually going to figure the pH first, and then based on what we know the scale represents, we can say whether it's acidic or alkaline. So negative log, again, of hydronium ion concentration. So that's the negative log of 4 times 10 to the -7. So hopefully you can input that in your calculator. If not, you're going to have to count all the zeros after the decimal place. So when I do that and apply the negative in front, I'm going to get a pH of 6.4. So that's less than 7. So therefore the pH of blood is 6.4, which is acidic. Okay. So a couple more questions on pH. Okay, it says orange juice has a pH of approximately 3. What is the concentration of hydronium ions in orange juice? So this is the opposite. So instead of, here's the hydronium ion concentrations, what's the pH? We're given the pH for this. We want to know the concentration of hydronium ions. Okay, so start off with the same equation. So in this case, pH is equal to a negative log of the concentration of hydronium. Okay, they gave us that it's actually a 3. Okay, sorry for my writing here. All right, so I can clear out that negative sign. I get -3 is equal to the log of this thing that we're trying to find. Okay, so actually, this is written in logarithmic form, obviously, but I'm going to change this into exponential form. So I'm going to solve for this. So if I want to solve for that, I can rewrite the equation as H, the concentration of hydronium, is equal to, now remember this is base 10, so I can, so that's the result. It's going to be base 10 to the power -3, and that can be written as 0.001. And if I want to put it in words, therefore hydronium ion concentration in orange juice, OJ, is 0.001. I'll put the units. Remember, this is always measured in moles per liter. And there I sound very scientific. So that's how you go backwards. Given the pH, what's the concentration? Okay, and then this last one, it says which has a greater concentration of hydronium ions, orange juice or tomato juice, and by how much? So I'm going to do a little table here. So I'm going to have tomato juice and orange juice. And I'm going to have the pH and the concentration here. So, based on what we've already discovered from the previous questions, we know the pH of tomato juice is 4. We know the pH of orange juice is 3. And the hydronium ion concentrations, well, we just got this one here, 0.001. And from the previous page, we do tomato juice was 0. It had one more 0. So the question is, which has a greater concentration? So don't be fooled by looking at the pH, because actually the higher the pH, the lower the concentration. Okay, so let's look at these numbers. You can definitely tell this is a higher number. So therefore, orange juice has a greater concentration of hydronium ions. And we could say by a factor of. Now there's two ways we can do this. I can do it as a ratio of the hydronium ions. So I'll put the higher one on the top, because that's the orange juice over the tomato juice. You can see this is actually 10 times bigger. So that number is equal to 10. Okay, so it's 10 times. So basically orange juice has 10 times more hydronium ions. But we could have looked at this and said the fact that we went up by a value of 1 on the scale, which means that's a difference of a factor of 10, because this is a log base 10. So we could have looked at that and also arrived at the same conclusion, but this is maybe more more obvious, because you just compare the ratios of the ions and get your scale factor that way. Okay, so that's quite a few questions on pH, probably more than you wanted to do. So look at decibel scale. So I actually included a little diagram here. I think it's from a textbook, but it basically has the scale. So what do these values for decibel actually mean? So you'd be surprised, like even a value of 20, which seems pretty high, that's a watch ticking, up to 30. So this would be quite a bit louder. Well, in terms of reference, that'd be a whisper in the library, refrigerator noise, rainfall. Okay, so these are pretty faint sounds. Then you get into loud car alarms, or alarm clocks, cars, motorcycles, horns, snowblowers, rock concerts, shotgun blast. So this is where basically you're doing damage to your eardrums. Okay, so this is relative numbers of decibel, just so you have that idea. And if you remember, we talked about the difference in two levels. So if we took two numbers off here, or something that was given to us, we could find the difference in the decibels, and that's going to eventually tell us the ratio of the sound intensities. Okay, so we'll either be solving for this ratio or for one of these values. Okay, those are the only variables. I don't think I've ever seen a question in this course where you have to solve for one of these two. It's usually the ratio of those two. Okay, So first question, how many times as intense as a whisper is the sound of a normal conversation? So I'm going to start off by putting my formula, and I know those are capital B's, but they're more like beta letters from the alphabet. So beta 2 minus beta 1 is equal to 10 log I2 over I1. So that's the ratio of the sound intensities. So what we need is to get the decibel levels for a whisper and normal conversation. So if you go back over here, so we already saw whisper. Whisper is 30 and normal conversation is 60. So obviously conversation is louder, so our 60 is our beta 2, our 30 is beta 1. Okay, so first thing we do here, subtract. We get 30 equals 10 log of the intensity ratio. Okay, now we can actually divide both sides by 10, so we get, I'll turn the sides around here, log of the ratios of intensity is equal to 3. So again, I'm going to turn this around, because if I want to solve for that, I'm going to turn it into exponential form. So I2 over I1, okay, this is exponential form, so it's the base to the exponent, so the base is 10, because that's a common log, 10 to the power 3, which is equal to 1,000. So therefore, a conversation sounds 1,000 times more intense than a whisper. So the hard part about this is just understanding, are they talking about intensity or the decibel level? Okay, so the intensity, it's the ratio of the intensities. So it's a certain noise will be this times more intense than another sound. Okay, and we can get that from the difference in the decibel readings. Okay, the next one we're actually, it's a different kind of solving question. So it says the sound level in normal city traffic is 85 decibels. Sound level while riding a snowmobile is about 32 times as intense. So it's the louder of the two sounds, obviously. What is the sound level while riding in a snowmobile in decibels? So if we start off with our formula, same as above. Okay, so this will be our snowmobile because it's the louder. So the snowmobile, we don't know. That's what we're trying to find. So we keep that as our beta 2. That's what we're going to actually solve for. But we do know that the traffic decibel level is 85. And we also know the ratio of sound intensity, 32 times. That replaces our ratio here. So that's log of 32. Okay, so if I want to isolate beta 2, I'm going to add 85 to both sides. Now, be careful here. You're not adding it to the 32 there, because the 32, you're taking the log. So you have to do this first and then add 85. Okay, if we do this, put this in a calculator, which you can definitely do, you're going to get beta 2 is equal to 100, approximately. And that tells you the decibel level of a snowmobile. Therefore, the sound level while riding a snowmobile is approximately 100 dB. And that's pretty loud. Okay, so that's how we work with the decibel scale. Like I said, you'll either be solving for a decibel level of one of the things you're comparing. So it's always about comparing, right, two different sounds. So these are the decibel levels. This is the ratio of the intensity. So in this case, we knew the intensity ratio. We knew one of the sound levels. We wanted to find the other one. In the previous example, we knew both of the sound levels, the decibel levels. What we wanted to find out was the intensity ratio. Okay, so it's probably going to be one of those two format questions. Okay, the last scale is the Richter scale. So this is the earthquake. Okay, so for some reason that's not in your key concepts, but it should be. It's one of the three formulas that you'll need to know. Now it's a little bit nicer than the last one. So the magnitude of an earthquake measured using the Richter scale, which is defined as the magnitude is equal to the log of I over IO. Okay, so what does that mean? I is the intensity of the earthquake being measured, and I0 is the intensity of standard low-level earthquake. That sounds confusing, but basically I0 or IO, that's like what we normally feel, the normal intensity level when there's not an earthquake. So even though you don't feel it, there is an intensity level. So it's the ratio of the earthquake being measured versus, the baseline of the earth movements. Okay, so let's try this out. So how many times as intense as a standard earthquake is an earthquake? Oh, I kind of doubled that there. Is an earthquake measuring 2.4 on the Richter scale. Okay, so let's start with our formula. M equals log I over IO. Okay, and that is that's the Richter scale number there. So we know it's a 2.4. Okay, and we've seen this before. So if we're trying to solve for that, we're going to change it over into exponential forms. So I'm solving for that. So I over IO is equal to, remember it's base 10, that's the exponent. So 10 to the power 2.4 is equal to 251.19. So therefore, an earthquake measuring 2.4 on the Richter scale is 251 times more intense than, I know they're saying a standard earthquake. That sounds like something heavy is going on, but that's just the regular earth movement. Okay. Okay, so that's fairly straightforward. So again, there's only two things that can be asked, either the intensity or the decibel. So this part B is going the other way. So they're giving us the intensity, and we want to know the magnitude or the Richter scale level. Okay, so M equals log I over IO. So M equals log of, and the intensity was 1,000. So log of 1,000, so base 10. So you could actually do this one in your head. So it's 10 to the power 3 will give you that Richter scale level. So therefore, an earthquake that is 1,000 times more intense of 3 on the Richter scale. Okay, so that's it. We've looked at all three applications: pH, the decibel sound scale, and the Richter scale for earthquakes. So you need to be able to answer the questions in the different directions like we've tried to practice here. So two of the variables, what's the value of the unknown variable still, okay? So a few questions to do from homework just to practice these, but again, it's just going to be these three applications. You have to know the formulas for them, and you have to know how to use them to answer the questions. Sometimes you saw plenty of examples where we changed from an equation in logarithm form back to its equivalent exponent form to solve for. If we're looking for what we're taking the log of, we're going to change it back. Okay, so that's it for today. In our next topics, we'll be looking at how to solve logarithmic equations. So there's going to be several techniques for that, so we'll break that down over a few lessons. Okay, have yourselves a good day.